some work which was done with graduate student at Weizmann, was Katz, Itai Rabinak, and Ran Budnik, who did most of the work here. Excellent group of young students. I'll talk about this phenomenon of shock breakouts. I'll try to explain what this is, why I think this phenomenon is interesting, and what the open questions are related to this subject. Okay, so as you know, massive stars end their life with supernova explosions. The core of the star collapses into a compact object, and some of the energy which is released is deposited in the envelope and ejects the envelope. The way the envelope is ejected is by a shock wave that goes from the core of the star all the way out to the surface. And the shock wave hits the envelope and gives it kinetic energy, which unbinds it. Models usually fail to do it, but we see that this happens. Now, the shock wave that goes through the envelope is what we call a radiation-mediated shock. It's different than normal shock waves in the laboratory that you're used to. And I'll say a lot about what this means later on. The edge of the star, the outer 10⁻³ solar masses of the star, is heated to keV temperatures. And it has been therefore expected for a long time that the emergence of the shock wave from the edge of the star would be accompanied by thermal X-ray emission. Okay? This has not been seen until about 2 years ago, because there's a short X-ray flash and you need a wide field X-ray monitor of the sky to catch it. First time you saw it is probably 2 years ago, and I'll say a few words about that. So now we have two examples, I guess, at least two solid examples, and maybe some more less solid examples. Following this X-ray flash, the envelope of the star begins expanding, and the optical depth of the envelope goes down. So the photosphere, the place from which photons escape, goes inward into the envelope. And as the envelope cools down and expands, this produces an early UV emission, which peaks on a daytime scale. Again, this has not been seen until 2 years ago. The triggering of the thermal X-rays allowed us for the first time to also see this UV emission. Normally, supernovae are detected days to weeks after the explosion, so all this has not been observed until recently. Now, if the massive star is surrounded by a wind, and massive stars do tend to be surrounded by massive winds, so it's the mass ejected by the star, then the breakout of this X-ray flash may take place as the shock wave goes through the wind surrounding the star instead as it goes through the edge of the star. And the interaction of the ejecta of the supernova, this part that was accelerated by the shock wave with the surrounding wind, produces long-term non-thermal X-ray and radio emission. Okay? So this is sort of chronologically what happens. I'll discuss each of these stages separately and tell you a little bit about the theory and the observations and what the open questions are and what we have learned. So first, what is a radiation-mediated shock? A shock wave is some, ideally it's described as a discontinuity into which fast fluid goes in, and fluid leaves this discontinuity at a slower speed. Some part of the kinetic energy is converted to thermal energy at the discontinuity. Okay? So in reality, of course, the transition is not a mathematical discontinuity. It takes place over a certain width. For shocks in the laboratory, the transition width is comparable to the mean-free path of Coulomb collisions of electrons and ions. Okay? So there is some fast plasma going into the shock wave. Okay? There's some shock transition and a slow plasma going out of the shock wave, which is heated to high temperature. Now, in the case of supernova shock waves that we're discussing, the scattering mechanism, the mechanism that converts part of the kinetic energy into thermal energy in this transition, is not Coulomb collisions of charged particles, but rather inverse Compton scattering of photons. So, under the conditions in which we're interested, the thermal energy density behind the shock wave is dominated by the radiation. Okay, so the particles carry little energy, all the energy is basically in the radiation. So what happens is that photons from the backstream here, from the downstream here, diffuse upward into the fast-moving plasma. So the fast electrons that approach the shock transition see these photons, they scatter them, and they lose energy and momentum by these scatterings. So they give some of their energy to the photons. The protons are coupled to the electrons by electrostatic forces, so they are decelerated as the electrons are decelerated. Okay? So the conversion of kinetic to thermal energy is through this inverse Compton scattering of the electrons, which slows down the plasma gradually. Now, the thickness of such a transition, of a radiation-mediated shock, is easy to estimate by comparing two time scales. One, there's some time that takes along which let's say the fast fluid elements that approach the shock cross the transition layer. This is simply the thickness of the shock divided by the velocity. Over this time scale, photons from the downstream should be able to diffuse upstream, otherwise they will not be able to decelerate the flow. Now, the diffusion time of photons, okay, this is the light crossing time of this region times the optical depth, times the number of scatterings across this width of the shock. Okay, so if the thickness of the shock in some optical depth units is delta divided by the mean free path, then the time that it takes photons to diffuse across this is larger than the light crossing time by this factor. Comparing the two, we find that the thickness of the shock wave in units of optical depth, thickness divided by the photon mean free path, is the speed of light divided by the shock velocity. So this is the thickness of the shock. Now, if we are considering now the case where the shock approaches the edge of the star, okay, then at the point where the optical depth ahead of the shock wave is comparable to C over V, okay, at that point the photons would escape, and this would produce the X-rays that we see, and also imply that the shock wave could no longer sustain itself. Okay? So at what mass fraction of the star would this happen? Okay, if we take the optical depth to be C over V, okay, then the mass is simply the area divided by the opacity. This is centimeters squared per gram, times the optical depth. As we'll see, for the shocks in which we are interested, C over V is not far from unity, so tau is going to be not far from 1. So this happens at 10 to the minus 8 solar masses if the stellar radius is 10 to the 12 centimeters. So this is a tiny fraction at the edge of the star. Okay? If instead the star is surrounded by a wind and the wind is optically thick, okay, then the shock wave would go through the edge of the star, it would go into the wind, and when the wind optical depth would drop below C over V, we would see this X-ray flash. And again, for the winds, we would use this parameterization of little m dot, which is the mass loss of the star divided by the wind velocity, normalized to typical parameters, which are 10 to the minus 5 solar mass per year and 1,000 kilometers squared per second, 1,000 kilometers per second, which are typical parameters for massive stellar winds. Okay, so again, in this case, okay, if the radius at which the breakout takes place is 10 to the 12 centimeters, okay, then you see that this little m dot, okay, should be approximately 1. Or if you take typical values for the mass loss for massive stars, the breakout is typically expected to be at 10 to the 12 centimeters. Okay? So maybe I should comment here that let's say red supergiants have radii which are 3 times 10 to the 12 centimeters. Blue supergiants have radii which are 3 times 10 to the 11 centimeters. These are typical type 2 progenitor stars, type 2 supernova progenitor stars, and Wolf-Rayet stars, which are even more massive, actually have smaller radii.
Yeah, super
This is a normal shock wave mediated by Coulomb collisions in the atmosphere. Nothing to do with that. And the Wolf-Rayet stars, which are even bigger, even more massive, are smaller, and they have radii of order of 10 to the 11 centimeters. Okay, so 10 to the 12 is a good number to work with. Okay, so it is easy to show that the density profile at the edge of the star is a power law. Okay, the density drops like some power of the distance from the edge of the star. Okay, this is because the gravity is almost constant in the edge of the star, and the index here of this power law depends on whether the envelope of the star is radiative or convective, whether the luminosity is carried by radiation or by convection. Okay, so it's 3 or 3/2, never mind. There are some similar solutions describing shock waves accelerating down such density gradients. So as the density drops, the shock wave accelerates, and these were found by Sakurai in the 50s. And if you interpolate between the set of Taylor solutions for decelerating shock wave and accelerating shock waves, you find that the velocity diverges near the edge of the star, with some power of the distance from the edge of the star. So the normalization is simply the square root of the energy of the explosion and the mass of the envelope, and it diverges near the edge of the star like this. Now the post-shock thermal energy density, if you have a shock with velocity v, okay, then the energy density of the plasma coming into the shock wave is rho v squared, and the energy density behind is comparable, in radiation, is comparable to this rho v squared times some numerical factor, of course, which depends on the quadratic index of the equation of state. Okay, so from these very simple relations, we immediately infer most of the things in which we are interested. Okay, so as the shock accelerates to the edge of the star, C over V decreases, okay, and the optical depth decreases. At some point, the optical depth of the star is going to be equal to C over V of the shock. And for this power law decrease of the density near the edge of the star, you can find the velocity, the maximum velocity to which the shock reaches. This is the point where the optical depth simply equals V over C, C over V. And you see that you get to mildly relativistic velocities for radii of 10 to the 12 centimeters with typical explosion parameters, 10 to the 51 ergs and 1 solar mass. Okay, so for typical stars, the velocity of the shock at breakout is mildly relativistic. Okay. Never mind about this. The temperature of the breakout from this balance rho v squared equals the energy density in radiation behind the shock. You get the temperature, and this is something like 0.2 keV. Okay, for 10 to the 12 centimeters. And you can also get the energy. The energy is simply the thermal energy contained in this narrow shell at the edge of the star, and this is 10 to the 46 ergs. Okay? Approximately 10 to the 46 ergs. Now, if breakout takes place in the wind instead of the edge of the star, and again, if it takes place at a radius of 10 to the 12 centimeters, okay, similar arguments give us again the temperature and the energy of the breakout, and you see that they are similar to these values. Okay, it doesn't really matter what the exact shape of the density profile is. The only important thing is the radius at which the optical depth reaches C over V. So again, a fraction of a keV and a few times 10 to the 46 ergs. And here gamma is the Lorentz factor associated with the velocity of the shock wave, and because it's mildly relativistic, gamma beta is going to be approximately 1. Okay? So now this is what was expected. We expected to see an X-ray flash, 3 times 10 to the 46 ergs with a temperature of something like 0.1 keV. Okay? And there is one consistency check that one can run. If you measure the energy and the temperature of the breakout, okay, these are two parameters, and you see that these two parameters, these two observables, depend on two model parameters, the radius of the breakout and the velocity of the shock. So you can infer both the radius and the velocity from the observed temperature and energy. And then the duration of this flash should simply be R over C. Okay? And of course you measure the duration, and it should be consistent with the radius that you infer from the energy and the temperature. Okay? Okay. This is the first part of the story. The second part of the story is the interaction of the fast shell of ejected from the star with the wind.
This is spherical.
Everything is spherical. If it's not, it's more complicated and it's more ugly. So I'll say a few words about it later. Then I wouldn't be able to write all this very simple formula. Now, as the fast shell that is ejected from the edge of the star plunges into the wind, it starts decelerating when it accumulates a mass in the wind which is comparable to the shell mass. So there's some characteristic deceleration time. Okay? If you take 10 to the 47 ergs as the characteristic energy of this breakout shell, okay? It's going to be tens of minutes. And as the shock wave, which is driven into the wind by the fast shell, propagates into the wind, this shock wave is now not a radiation-mediated shock. It's a collisional shock. I will not discuss it in any detail. But it would accelerate electrons to high energies, and these electrons would emit synchrotron and inverse Compton radiation. The synchrotron emission from these electrons is expected to be around 10 to the 40 ergs per second, and should be dropping like 1 over the time. If the energy density in the light produced by the supernova itself is larger than the energy density in the magnetic field generated in the shock wave, then the electrons actually lose most of their energy to inverse Compton scattering of supernova photons. And then the luminosity is going to be similar, 10 to the 40 ergs per second on a day time scale, but it would be dropping slightly at a slightly slower rate, like T2 minus 2/3. And this is for supernova luminosity, which is characteristic at that time of 10 to the 42 ergs per second. Okay, so we expect this non-thermal X-ray emission from this synchrotron or inverse Compton of the electrons produced by the shock wave driven into the wind. And this is supposed to follow the thermal X-ray emission. So, what did we see? So the clean case, I think, that we have is the case of supernova 2008D, okay, which is fairly recent. The Swift satellite was looking at some galaxy because there was another supernova that went off at that galaxy, and by some amazing chance, another supernova went off at the same galaxy. This is one in, I don't know how many chance, but it happened. So it saw this, and since it was looking at that galaxy, it saw the X-ray flash, and since Swift also has UV and optical telescopes, it automatically stood to that position, and it measured the early UV emission. Okay? So what did they see? We got an X-ray flash of 3 times 10 to the 46 ergs, which is exactly what should be the energy. The duration of the flash was some 30 seconds, and C times 30 is 10 to the 12 centimeters, which is also reasonable. The size of the star, the progenitor star, the progenitor of the supernova is almost certainly a compact Wolf-Rayet object. So the radius of this star is 10 to the 11 centimeters. So we infer that the breakout took place within the wind surrounding this object. Again, and as you saw from the formula in the first slide, it's reasonable to obtain breakout at 20 to 12 centimeters from a massive wind surrounding a massive star.
Sorry, how did you know the progenitor?
This is from later observations where you look at the spectra of the ejector. So you infer the composition, the energy, and so on. It's not from these observations. Although, I'll show you that you can infer this radius also from these observations, but that's a separate issue.
Excuse me, the length of the burst I thought was quite a bit longer, about 100 seconds or something like that, which I think is a bit of a problem actually.
Well, so it depends on how you measure
the e-folding.
So there was, the rise was about 30 seconds, and the e-folding is also 30 seconds. And then it decays on a longer time scale.
The e-folding was 100 seconds, I think.
I think it's 30, but what's the factor of 3? Okay, but I still think it's 30. What about the non-thermal part of the wind that we expect? If there is a wind, there should be a non-thermal X-ray emission, but and also radio emission from the synchrotron of these electrons. And this has been observed. The X-ray luminosity, the non-thermal X-ray luminosity that was observed on a day time scale was 10 to the 40 ergs per second, dropping like 10 to the minus 2/3 roughly. And this is exactly what we expect from this wind interaction. Okay? And from these observations, from the X-ray and the radio observations, we can also measure the density of the wind independently of the breakout radius. And this also comes out to be this little m dot of about 1. So the 10 to the minus 5 solar mass per year and 1,000 kilometers per second. So this is all consistent. We can also measure the velocity of the shell generating this X-ray and radio emission, and it comes out to be 0.3 C, which is what we expect for these breakouts. So far everything seems to be...
But the mass loss depends on what you assume about the epsilon E's and B's.
No. Because since we have the radio observations, we can actually calibrate.
Yes, but the radio emission depends on the epsilons.
But we have both the radio and the X-rays. If from the radio alone, you're right, you cannot measure this. But from the radio and X-rays together, you can measure it.
What assumptions do you make about magnetic field in the market?
So what we assume here is that some fraction of the energy goes into magnetic field, some fraction goes into electrons. And so you have two free parameters, and if you have radio and X-ray observations, you can calculate.
So what fractions do you use? What numbers?
The numbers come out to be around the equipartition for both. Okay, but this is not the main point. We expected the thermal X-ray, the X-rays to be thermal with a temperature of 0.1 keV. Now, had the X-rays been thermal at 0.1 keV, Swift would not have seen this burst to begin with. Okay, so obviously this was not what was observed. The X-ray spectrum was not thermal. It was a power law extending to high energies, with roughly 1 over. So now with number of photons dropping like 1 of the energy of the photon square. Okay, so this was the big problem for this case. So this is a major inconsistency with what we expected, or at least some of us expected, let's say. So the spectrum doesn't fit. So what are the possible explanations? So one possible explanation was to say, okay, let's pretend it's thermal. Sorry, that's what you did. Let's pretend it's thermal, then everything is okay. Another sort of interpretation was that, okay, the spectrum is not thermal, so it cannot be a breakout. We have to have a relativistic jet going through the star and all these stories. This is very nice, of course, because we cannot calculate, we don't know how to calculate anything about those jets, so they can produce whatever you want. That's very good. Slight problem with this is that we have, this object was actually resolved, marginally resolved by the VLBI observations, and we know that there was no highly relativistic component in this object with a velocity larger than 0.6. So, although theoretically it's very nice.
This is the velocity of the head, not necessarily.
Yeah. So
what is the relativistic jet? You're referring to the velocity of the head or the alpha itself?
The velocity of the head of the jet. Yeah. If there was such a fast shell going into the wind producing the radio, the size would have been larger. So you can argue maybe that it was highly collimated and you lost the energy and then accelerated. But in fact, I think that, okay, and there's another possible explanation, which is we don't understand something about the physics of the shock breakout, which causes the spectrum to be non-thermal. Okay? And from the way I presented it, you know, I guess, what the right answer is. And let me try to explain why. So for this, we need to look a little bit closer into the physics of those radiation-mediated shock waves. Again, we have a fast electron-proton plasma, roughly, going into this transition of the shock wave, going out at a slower velocity at a high temperature. Okay. Now, the shock waves in which we are interested are mildly relativistic. Solutions for non-relativistic shock waves, radiation-mediated shock waves, have been obtained in the 70s, late 70s by Weaver. the reason that those solutions are inapplicable to the mildly relativistic and relativistic case, or there are several reasons why they're not applicable. First, as we already saw, the thickness of the shockwave in units of optical depth, the number of photon scatterings, is C over V. So when V is much smaller than C, the thickness of the shockwave is large. There are many photon scatterings. So you can use a diffusion approximation to describe the photon population. Now, when the shock velocity gets close to C, you can no longer use the diffusion approximation. There's a large gradient here over a mean-free path of the photon. So you cannot use the diffusion approximation. Also, the electrons are heated up to mildly relativistic temperatures, as I'll show you. And in each collision of a photon and an electron, you change the photon momentum by a large number. So again, you cannot use diffusion for the spatial distribution, and also not for the momentum distribution of the photon. Okay? This implies that you need to solve the transport equation for this problem, and solving the transport equation is very difficult, and this has not been done. Okay, and an additional complication is that when you get to higher temperatures, you start having all these relativistic processes. You produce pairs, you have triple Compton, and all sorts of nasty stuff that prevents you from from obtaining a simple solution. Okay. Now, as I'll show you in a minute, an additional complication is that the electrons are heated in this transition layer to temperatures which are much higher than the downstream temperature of the radiation. So they actually get to temperatures of mc squared at a velocity which is much smaller than the speed of light. Already at 0.1 c or so, the electrons become relativistic. Okay? So all the solutions that were available were not valid for velocities larger than 0.1 c, and since the breakpoints in which we are interested are that regime, they are not applicable to the problem in which we are interested. So we have actually solved this problem, actually exactly. This is the Bas Katz and Ran Budnik. So we have exact solution of this radiation radiated shockwave in the relativistic limit, but I will not go into the exact solution. I'll try just to explain what the major ingredients of the physics are. So this is a solution of the shock profile for V over C of a quarter. Okay, what you see here, this is the velocity normalized to the speed of light. Okay, you see the fast incoming plasma, and it goes at roughly 0.3 or the sort of 3 at the back of the shock. Okay, this is the shock transition layer, the optical depth. Okay, this is in units of optical depth. So the optical depth of the transition is a few, as we expect. Now, the downstream temperature of the plasma, okay, in this case is of order 0.1 keV, which is what we expect. But as you see, the temperature in the transition layer is much, much higher. And why does this happen? As the electrons go through the transition, the shock transition, they need to produce the energy density in radiation that carries basically all the energy and momentum in the downstream of the flow. Okay, so they have some limited time to produce enough energy and momentum in radiation. Now, if they were heated only to the downstream temperature, they wouldn't have enough time to produce those photons. So what happens instead is they are heated to much higher temperatures, okay, so that they produce energy in radiation at a much higher rate, okay, to produce exactly the correct amount of energy across the shock transition. Now, the radiation that's produced here is not thermal. Okay, the electrons are roughly thermal because they do have Coulomb collision interactions, but the radiation is not thermal. You produce a sort of Bose-Einstein distribution of photons with a finite chemical potential, if you want. So you have a small number of photons with much higher temperature, much higher energy compared to the number of photons and energy that you have in the downstream. And what happens here is that there is a slow and gradual process of thermalization. You produce a small number of photons with very high energy, and as you go to the downstream, you produce more and more low energy photons, and the radiation thermalizes to the downstream value. Okay? And it's actually fairly easy to estimate the temperature to which you heat up the radiation. And this is easy to do. You compare, as I said, you need to produce the energy density and radiation here. So how do we estimate the number density of photons in the transition layer? You take the production rate times the diffusion time across this diffusion layer, and this is the number density of photons that you have there. Okay, the production rate is from Bremsstrahlung, and the diffusion time is the optical depth times C over V. Okay, so this is what's written here. There's one slight complication that you need to be aware of. This is the Bremsstrahlung emission. So you see the usual expression, number of electrons squared, alpha time the fine structural constant times the Thomson cross-section, times the square root of the mass divided by the temperature, but times this correction, lambda. The point, there's some subtle point here. The number of photons which are produced by the Bremsstrahlung process diverges as you go to low frequencies. Now you say, okay, I don't care about all these low energy photons because they don't carry energy. The energy converges. However, some of these low energy photons will be upscattered to high energies by inverse Compton scattering of the electrons, because the electrons, okay, if they are heated to a minor relativistic energy, they could take some of the low energy photons and upscatter them all the way up to the high energy. So you should count these photons as well. So the question is, okay, how far down should I go in counting the Bremsstrahlung photons? So the answer is, when this low energy photons, so you take a low energy photon and it is being scattered upward in energy, it has some probability of being reabsorbed by inverse Bremsstrahlung. Okay? So you need to count all the photons that have enough time to be upscattered all the way up to the energy of the photon before they are absorbed by inverse Bremsstrahlung. And this sets this factor lambda. Okay? If you don't take it into account, you get wrong results. So, okay, you take this lambda. We know what the number density of photons is, and we should compare number density of photons times the temperature of the photons, which is the temperature of the electrons, should be equal to the energy density in radiation in the downstream. And this immediately gives us a relation between the temperature and the velocity of the shock. Okay? And I wrote here the velocity of the shock in terms of the temperature because you see that the temperature is an extremely steep function of the velocity, and when you are using such very simple arguments to derive the results, you should be careful about small factors here when you take it to the 8th power. So for a temperature of 10 keV, the shock velocity should be approximately 0.2 C, and that's very robust, okay, because of this high power. Now this is independent of the number density of the plasma. Okay? The downstream temperature is dependent on the number density of the plasma, because the energy density in the downstream is simply the density times V squared. But the temperature here in the transition layer is independent of the density of the plasma. This is easily inferred from these relations. Okay? The number density drops out here. So, for low densities, okay, in which we are interested, we have a direct relation between the velocity and the temperature. Okay? And you see that the prediction of this, if you solve it correctly, you find that if the shock velocity is 0.1, 0.2 C, the photons that come out of this are not thermal and they have characteristic energies of tens of keV. Okay? And if the velocity is slightly higher, it would be hundreds of keV. So our expectation should have been that we should see non-thermal spectrum, tens of keVs, and this is exactly what we saw. Okay, there are all sorts of details with the ratio of this thermalization length compared to the transition and so on. All can be derived from these simple arguments.
Why are you saying non-thermal spectrum? Because you're still getting like multiple Compton scattering, and you'll get basically Wien spectrum.
No. So you get a Bose-Einstein, as I said.
What's the difference?
Okay. One difference is of course crucial, because if you say that the luminosity is 4 pi r squared times sigma t to the 4.
No, you have just color temperature, which is order of magnitude higher of the effective temperature. Yeah. So, but it still looks
so the
like
radius. Thermal. So you need to be very careful.
No, but I mean, it looks like thermal.
It looks like thermal.
So, and if you observe the power law with index 2, it's not thermal, right?
So the next step is, which I will get in the next slide, but let me explain it here already. So what is the spectrum of radiation that escapes from this as the shock wave gets into the edge of the star? So first you see these photons at this temperature. then you see these photons at this temperature, and then you see these photons at this temperature. Okay? And then you are cut off because of adiabatic losses. And we don't have an exact solution for this problem because it's difficult enough to solve the transport equation for the steady shock. What happens as the shock gets to the edge of the star, it is non-steady and it evolves. But roughly, you expect to get equal energy per logarithmic energy beams of the photons down to a cutoff temperature that you can estimate based on the expansion, based on the adiabatic expansion losses.
And also that
So the spectrum that you generally expect is a flat spectrum as was observed, although we don't have an exact calculation.
So basically, you predict that it will be cut off at 30 kV or something.
No, for this case, 30?
Yeah, because you have the highest temperature, which is like 10.
Yeah. At the highest energy, yeah, the cutoff should be at some tens of keV, but note that this is extremely sensitive to the velocity. If you, okay, let me say a few words about the cutoff energy. Now, so the temperature, the transition is extremely sensitive to the velocity and it rises very sharply, but it reaches at most 200 keV. And why is that? This is due to electron-positron pair production. Okay, so as the temperature of the electrons reaches a fraction of an MeV, there's an equilibrium pair production. So the ratio of photons and positrons is simply mc squared divided by the temperature. And then these are the electrons and positrons, the positrons that produce the photons in this equation. Okay, so here now this is not the density of the plasma, it's the density of the positrons. So from this relation you get another relation between the number density of photons and positrons. Okay, this goes like positron squared divided by positron, so you get a ratio between the photons and the positron density. Okay, this is what's written here. Okay, and if you combine the two, you find that the temperature, the maximum temperature that you reach when the velocity of the shock goes to C is 200 keV. Okay, so it's very sensitive to the shock velocity, but there's a clear prediction that this process will not produce photons with energies larger than half an MeV. There should be always a cutoff here.
I mean, the Klein Shima is also roughly.
The Klein Shima, sorry, Klein Shima is taken
so
in.
much, but I think that one point is that here you assume that the upstream is completely cold. If you conduct photons, enough photons, then essentially you can get actually power.
What do you mean convect?
Suppose that your wind has, I mean, this runs into a wind or in the envelope. If this has a soft energy radiation, which is produced by some other process.
Some other process is a different.
No, but
I'm talking about real. I mean, solution. There's a very simple clean problem which has a very simple clean solution.
I'm saying take a different initial condition that your
The upstream is hot.
the upstream is.
But the upstream, okay. I don't want to go into this because the energy density in the shockwave is huge.
Then you can get actually a parallel. Because then the Blanford-Pine process.
No. The Blanford-Pine process does not operate here.
If your upstream is conducting enough photons.
So there was some work of Blanford and Payne in the 80s about the possibility of photons being backward and forward scattered between across the shockwave.
This is
short of a Fermi type acceleration of photons. This process works as long as the photons do not lose energy by scattering the electrons. So it applies only to temperatures not exceeding a few 10 electron volts. It's completely negligible here because here the photons they cannot be accelerated because they lose their energy by Compton scattering of the electrons. So what you get is always this wind. This wind, you get sort of
if
a
you
wind
conduct
spectrum.
enough soft photons, then you will get power.
Okay, no, you will not, but we can argue about this more later. Okay, so I think we have basically a solution of this problem. My time is very, very short. So, but this is because of Amir.
But you can subtract this time, so you can add
Can we
it.
subtract it?
Okay,
So I think we have a nice explanation of this particular case. But maybe the more important conclusion is that, as you saw, for stars which are not too large, not larger than 10 to the 12 centimeters, you typically expect these fast shock breakouts. So most of the supernovae, which are produced by Wolf-Rayet and blue supergiant progenitors, okay, should have this component. They should all show these X-ray flashes with tens to hundreds of keV photons. Okay. Open issues. Okay, so this is something that I already discussed when I answered your question. We only have a solution for the steady state. And in order to really calculate the spectrum of the escaping radiation, you need to calculate in detail the evolution of the shockwave as it goes through the edge of the star. We haven't done it, so we have some hand-wavy calculations, but we are planning to do this as well. And, okay, transition to collisional, collisionless. I would skip this. This is also interesting, but no time, sorry. Okay, now, actually, our work on this problem was triggered by an earlier event in 2006, where there has been this case where thermal X-ray flash was observed. In that case, it was thermal plus a non-thermal tail at 0.2 keV, which seems like something that you expect from the shock breakout. In that case, the energy was much, much larger, and the duration was much, much longer. And also in that case, we observed long-term non-thermal X-ray emission, which is consistent with interaction with the wind. And again, the luminosity here was significantly larger. So if you assume that this is a breakout, you take the temperature and the energy to infer the radius and the velocity, you find a significantly larger radius and a significantly larger velocity, 0.8 c, and a radius of almost 10 to the 13 centimeters. So this has to be, if it is a breakout, it has to be a very massive wind, providing a large optical depth out to almost 10 to the 13 centimeters. Now the long-term X-rays are consistent with this. Okay, so if you put in so much energy in the breakout, okay, then the inverse Compton luminosity of the supernova photons give you the non-thermal X-ray luminosity that was observed. Okay, so this seems to work except for one major problem. The radius here, 10 to 13 centimeters, should have produced a few hundred-second X-ray flash, but the duration of the flash was significantly larger, a few thousand seconds. Okay, so this is a problem in this case. We don't have a clear solution in this case for explaining this long duration. One possibility is that the explosion was highly aspherical, so that the shock reaches the edge. Remember, the shock takes several hours to traverse the star. Okay, so if the explosion is not spherical, in principle, you could stretch the signal on the timescale of hours. But this is easy to say. I don't have a calculation to show this. And we should produce this. But there is a problem. So one sort of explanation is that the explosion is not spherical, and we do have clear evidence in later evolution of this event that the explosion was aspherical. Again, the other explanation is having a jet. Again, because the jet is something free, you can put in whatever duration, spectrum, or whatever. Well, for this case, although, it is impossible to explain both the X-ray and the radio in the jet model. Okay? So the jet also cannot explain it, even though you can do almost everything that you want to do. But the main thing is this duration, which remains an open issue. Now I want to comment on another event. So the first association of a gamma ray burst with a supernova was this 1998 BW supernova associated with the 08 or 425 GRB. Sorry?
98.
Yeah, 98, of course. If it were 10 years later, it would be much more interesting. No, right, so it's 98. Okay, now in this case, we saw a non-thermal spectrum, 10 to the 48 Hz, with a cutoff of 200 keV. So this could be produced by this radiation-mediated shockwave. The long-term X-ray and radio observations of this event, of the interaction with the wind, also give us a few times 10 to the 49 Hz with a velocity of 0.8 c. In this case, the mass loss of this wind is much lower than the case of 06 AJ. Okay? So these are very similar parameters to those inferred for O6AJ. So a reasonable proposition is that maybe all the low luminosity GRBs, there are a few of them, with this energy standard 48 or so, maybe they're all produced by fast shock breakouts with this velocity. The main challenge to this picture is to explain how you dump so much energy into such a fast shell. In a normal supernova explosion, the fraction of energy that goes to this fast to 0.8 C shell is something like 10 to the minus 5 or 10 to the minus 6. Here we need to dump something like 10 to the minus 2 of the energy. And this is, we don't know how to do this. Okay? So, but this is regardless of this association. We had two events for which we know that we have such a fast shell, and we need to come up with an explanation. If there is an explanation for that, then it might explain all the low luminosity GRBs. Again, this, the answer to this question might be related to the anisotropy of the explosion. If you have a faster jet trying to penetrate through the star, maybe it can do the job, but again, we don't have any calculations to show this. Okay, so if the scenario that I described is correct, we expect that all these low luminosity GRBs would have smooth light curves. This is just seeing the edge of the star. Should have cutoff energies of about 200 keV and should show no relativistic jets. This is actually true for all those associations. So maybe it's.
What do you mean show? How do you see relativistic jets in this?
So for 98 BW, for example, the ejector was monitored in radio for 7 years.
Yeah.
So had there been any significant energy in a relativistic jet, it would be seen.
Yeah,
So we know
not
that.
Well, I'll talk about this in a minute.
Not according.
Okay, maybe. Yeah, you can. Okay, maybe you can argue that with a very low density, you don't decelerate it, and it's pointing out away from you, and so on. But again, the fact having no evidence for a jet is certainly not an evidence for a jet. But the main challenge for this is that again, we need to dump a lot of energy, like 1% of the supernova energy, in this fast shell, and we don't know how this happens. Although we know it happens, we don't know how. Okay, now I want to say just a couple of words about the UV optical emission. Okay, you take this ejector that was heated to a keV temperature, you let it expand, the temperature goes down, the photosphere goes inwards, I mean, the radius goes outwards, but in terms of mass, it goes inwards. And, okay, so this is how the mass of the outer shell at which the photosphere sits evolves with time. This is the effective temperature. This is the color temperature that you expect to see. Okay, so the temperature that you see is somewhat higher than the temperature of the photosphere because photons diffuse up, never mind. All sorts of complications. And this is the luminosity that you expect to see. Okay? Two points that I would like to emphasize here. The effective temperature, or color temperature that you see after some time, let's say 1 day, depends almost entirely on the radius of the progenitor. It's independent on the energy and mass of the envelope. Okay? So if you measure the temperature at some time, you essentially know the radius of the progenitor. Almost. Some complications. There's a kappa that sits here in the equation. Okay? The opacity becomes complicated when the temperature is of order 1 electron volts. So you have to be careful when you do this exercise. And I will not go into this anymore. However, if you have, let's say, hydrogen stars, so not this compact object that I have shown you, but maybe larger objects which have hydrogen, hydrogen remains ionized at those temperatures, so the opacity is simple, and it should, the emission should be simply described by these equations. Now, following the two detection of the X-rays and the early UV emission from O6AJ and O8D, Gazzari et al. And also Shawinski et al. Went and looked at the GALEX data to look for early UV emission from non-supernova. Okay, so they went back into the data and looked at the positions of non-supernova and searched for the early optical UV emission. And they found two cases where this early optical UV emission had been observed. Okay, so what you see here, these are the data points in two bands, far and near UV, the black and the magenta sort of. The black and this wrinkled black and magenta curves are the results of detailed numerical simulations that they've carried with radiation transport and so on for calculating the emission from the expanding envelope. And the solid nice curves are what you obtain from this simple formula that I've shown you in the earlier slide. Okay? So this is simply this. So you don't need all these numerical calculations and so on. It's really very simple. Actually, they've also shifted their data by 1.5 magnitude to fit the observations, and we don't do that. Okay, so in principle, you have a very simple model that should describe the early optical UV emission. And based on this, you actually can infer the radius of the progenitor and also the composition. Okay? So you know that this star had to be hydrogen, because otherwise it would have recombined. And also, you know the radius, because you see that you fit it from the observed temperature. Okay? So there should be many more of these. So all the supernovae should show this. All red supergiants, blue supergiant, whatever, they all should show this. The blue supergiant and Wolf-Rayet progenitors should show also the X-ray emission that I discussed earlier. And this is providing us with a completely new handle on the physics of the supernova, because so far we have not been able to observe this. We couldn't infer the radius of the star and the surface composition of the star and so on. And this provides us very important new constraints on models. I'll skip this because I'm running out of time. Transrelativistic, never mind. I'll go to the summary. And I'll almost be on time. So, first of all, I've shown you that there's some interesting physics in fast radiation-mediated shock waves that produces very high energy, much higher energy photons than were expected. And we expect such breakouts of fast radiation-mediated shock waves in all the Wolf-Rayet and blue supergiant progenitors. Okay, so this should be a common property. We have one very clean example, which is this 08D supernova. And some open questions there are: an exact calculation of the spectrum requires a solution of the non-steady shock evolution, which we are working on, we don't have it yet. The collision and the collisionless transition I didn't have time to discuss, so it might produce high energy radiations and neutrinos for Perolov, but okay, I didn't have time to touch this. Now, low luminosity GRBs, in principle, they might all be such radiation breakouts. So they have the necessary characteristics. They have smooth light curves. They have spectra that are cut off at around 200 keV, which is the upper limit to which you can reach with this type of physics, if the shock is not highly relativistic, of course. The main challenge here for explaining those is explaining how you dump 1% of the supernova energy in a 0.8C shell. Okay, this is something which is solved. We have a simple model for the UV optical breakout, and I mentioned the complications with opacity and composition. And now, two last comments. If all these supernovae are accompanied by these X-ray flashes, then in principle you can think of supernova survey which triggers on those X-rays. So you can think of a wide field X-ray monitor that would trigger on this signature. And this is very important because it gives you the supernova at the explosion time. If you want to detect gravitational waves or neutrinos, it really narrows the window of explosion time, so it reduces the background. It provides a much stringent constraint on the explosion mechanism because you know exactly the explosion time. And actually, there was a Japanese satellite, not satellite, there was a Japanese detector called MAXI, which is supposed to go up on the International Space Station. To detect, I mean, if it flies and it works to specifications, a few of these every year. Okay, a few of these, maybe 10 of these every year. Okay, I think I've said all the important things. So it's okay.
Thank you, Eli. Questions? Yeah, plus.
There's been some hydro calculations which actually calculate the shock breakout, including the Compton scattering and so on by these old ones by Kleiner, Chevalier, and Michelnik and Joseph from the 1970s. What's different from their calculations, and what did they not include, which you have here?
Okay.
But they, for example, they did find this very different color temperature with a factor 2 or 3 higher than the
So, as they say, an excellent question.
Okay, good.
So, first of all, let me say a few things. Let me start before getting into this. One case which was studied extensively was 87A. The problem is that 87A was a very weak explosion for which the shock velocity is not expected to reach 0.1c. So even if
it was 50,000 kilometers per second, the
Right.
highest, it's
Right.
0.2.
50,000,
Yeah. That's what you directly observed from the spectrum. You probably had a velocity which was higher than that.
so
That's from the line.
16C.
Line width.
So it's just below this 0.2C where you get 10 keV. So even if all the calculations were correct, I don't think they should have seen this effect. Okay. Now, there have been other calculations that you might think should have shown this effect. The problem is that everything that they found in those calculations are simply numerical artifacts. So the Kleiner Chevalier calculations didn't really solve the shock structure. They have artificial viscosity.
These
So-
are relativistic calculations? These are relativistic or not?
No, it's not really relativistic, but this is for 87A, for example, which reaches this. So if we look first at this, so they have, you see that they have a non-thermal spectrum with this small bump here, but this bump is simply produced by the artificial viscosity. There's no physics included. The Hensman and Bauer's calculations, they seem to have a gas temperature much higher than the radiation temperature at the transition. And this is, of course, incorrect because the gas and the electrons are very tightly coupled. The reason they got this overshoot in the radiation and not in the electrons is that they didn't calculate the Compton pooling of the electrons, of the radiation. Okay. So they have both artificial viscosity and no Compton interaction. So these calculations are simply not adequate to capture the physics which is relevant for what we are talking about.
But what about these Michelnik and Yoshin calculations, which actually did include the Compton?
Right. So then
These are antique calculations, but still.
actually also some calculations of Blinikov and so on. So their calculations are okay. They did not look at fast shocks. Maybe, I don't know. I don't know if the calculations are correct or not. In principle, had they looked at very fast shock, maybe they would have seen it. But they haven't. And these calculations were simply, they didn't include the correct physics.
They high enough resolution?
I don't know what the resolution is and so on. So in principle, I mean, if you have a code that correctly solves the transport equation,
But it offers of the aerodynamics.
Yeah.
It's aerodynamic code, so.
of course, yeah, should
I think the problem with the Ensman-Burras and Blinikovs is that I don't think they really included the Compton scattering, the inelastic effects. So they treated just as scattering.
Blinikov says, at least in his paper, that he includes the inelastic Compton scattering.
I'm not sure.
I'm not sure that he includes it, but I'm sure that he says it.
Yeah.
So, but in any case, it's the shock velocity that he calculated
No, that's
is,
good.
is,
That's
is, is
probably
too,
low.
it
It was
is
for
too low.
instance.
It fits exactly with the predictions of this model, but for the low velocities. So,
But I mean, one comment is also that for 87A, that was actually a case where you did observe the UV and you had very good constraints on the shock breakout. But that is a somewhat high, lower velocity.
somewhat low velocities. That's right. Yeah.
Not very much. But
Yeah, you're right.
and these calculations were intended for that case. Yes, my burrows.
Yeah, for this, yeah, for exactly this case, for 87.
In principle, this can hold, if you have in the, prompt emission phase, forget about the breakout, this, no? If you form shocks, in the coasting region where the optical depth is large, then in principle you should also get emission-mediated shock there, right?
Again, if in GRVs,
In the prompt phase,
in the prompt phase,
I mean, the common wisdom is that the shock are somehow produced when the optical depth is small,
right,
but they can form in the coasting region.
you're right.
And then this, so there's some evolutionary consequences of this.
I think you're right. Yeah, I think in principle, the very simple-minded calculations of what happens in the antenna shocks of GRVs are really simple-minded. But we haven't looked at that. In principle,
No questions.
Just one idea. Just explain me, please. You, when you transfer to your simple model, as you call it simple, it's not so simple. But anyway,
Simple as
you
it
told
gets.
that diffusion should not work properly when you consider these breakouts with a shock.
right,
As a gamma beta about 1.
right.
But still you are using, seems to me, diffusion time as a characteristic time for
Yeah.
your how comes? How can you explain this?
Yeah, you're absolutely right. Someone was listening to this.
Yeah, exactly.
So you're absolutely right. So if we can only say something analytically about the properties of the flow, let's say from this point onward, okay? So here, in this regime, where the density of the plasma has been increased by a factor of 7 or so by the flow, okay? The optical depth here is like 1 or 2, but here it becomes sort of 20 or so. So diffusion approximation is certainly valid for the formalization length, and it is valid beyond the peak of the temperature. Okay. Now, if you ask me what the temperature profile is ahead of the shock wave, then you cannot use the diffusion approximation. But there are other approximations that you can use to actually reproduce this also analytically. But all these arguments that I've used are valid only beyond the peak of the temperature. But still, okay, I'm using the arguments beyond the peak to calculate the temperature at the peak, which is roughly okay. And you see here, this is the simple analytic. This line is the simple analytic expression, and this is the exact solution. You're right.
I'm still a bit confused about the length of the 08D burst, because I'm quite sure it was 100 seconds, because that was really what caused us a big problem to explain, because the luminosity and the temperature was quite consistent with the shock breakout, but the length was much longer than we do expect for something like a Wolf-Rayet star. We got a radius of about 8 times 10 to the 11 centimeters or something like that, which is sort of okay for a Wolf-Rayet star, but that does correspond to the length of the burst of about 30 seconds or something like that. So say it was at least a factor 3 larger than that, and that's not at all trivial to get actually. And I think even if your physics is a bit different, I mean the radius you have is roughly the same, so you should have the same problem with the length.
No, the radius is very different if you assume 4 pi r squared sigma t to the 4th power. Okay, then you get the radius is completely off.
No, but
because the temperature is much higher.
I mean, we use the radiation temperature, which was a factor of 3 larger than the effective temperature, which comes in
But there was not what temperature. But there was no temperature. What temperature did you just assume some number? Like, I don't know, 5
Well,
degrees?
consistent with the observations, which is, I mean, the observations actually consistent both with the power law and sort of, quote, thermal spectrum of black hole, modified black body.
You could add maybe you could add the thermal spectrum to the power law, but there's no need for it in the data. But anyway,
No, but there's no, I mean, it's consistent, and that's what's enough. I mean, the side square is less than 1. Reduced.
But since the radius goes like the temperature squared, it's very sensitive to what you assume about the
Oh,
temperature.
yes.
And I'm saying that there's no temperature here. This is to calculate the radius. You need to use this, this solution.
So what is the radius you're getting?
So this is about 10 to the 12 centimeters. So,
Yes.
and I agree that this is consistent with the 30 seconds. My recollection was that 30 seconds is consistent, but if you have a different, if you have a different recollection, we can maybe we can look at it and check what. There's no point in arguing about the facts.
No, but I think that.
And again, as I said, we don't.
For this, and I mean, our
don't
ways
really
of
have-
explaining that if you had a scattering shell outside, which is not thermalized in the spectrum but just scatters, then you could explain something like that. And there are indications from some other type 1c supernovae that you do have a very dense circumstellar medium, much denser than from a standard width. But there also pulsational stabilities acting, which could explain something like that. And I think it's quite clear that we don't understand this very last stage just before the explosion. I think that's interesting indications. But there are indications also from other 1Cs that you have these very dense shells.
I completely agree that it might be much more messy, the density just around the star and so on. But I think my view is that it can all be explained by very simple pictures. I don't want to complicate it. Although I said, and I will repeat it, that we don't really have an exact calculation of the spectrum and the temporal behavior of the escaping radiation. Okay? Because this really requires a calculation of the evolution of the shock waves that goes through the edge of the star. We don't have it. We just have a rough estimate. So,
But the time scale will still be a problem.
But the time scale might be a problem if it's.
Because that's
if
it's just like
so
crossing.
we can look at it.
And what degree of anisotropy? You can put some constraint on the degree of anisotropy.
In this case,
In the expansion, the shock expansion inside the star.
for OHD or for the 6AJ.
Well, you can put it in the model, for example. You should be able to estimate the anisotropy, which basically spoils your equation for the duration.
For the duration.
Yes.
Right.
You should get this number correctly.
I'm not sure that it's so easy to get this number. The only thing that I can say is that the time scale is hours. So it's easy to get, surely tens of seconds, it's easy. But can you actually get the OH6AJ in hours? That I'm not sure. I don't know exactly how to estimate this. But I don't have any good, I don't know, a simple intuition beyond saying that I know that the time scale is hours, so I can imagine that if I did some complicated structure, I could try to reach hours spread. But I don't know how to, I don't have a good way of going beyond, really quantitatively beyond that. Maybe there's a simple way.
Okay, I think we had enough questions. Thank you, Eli.